Hello everyone, I'm back again with another video about reading XADC data, this time via AXI with interrupt. This is the third method. If you haven't had a chance to visit my YouTube channel, I have provided the address here. Please go and visit this channel in order to find some tutorial on SOC design with some simple examples, especially in the next slide. I have given the address to the first and second method. The first method was hardware-based XADC test. The video was uploaded in this address, and also the second one is reading XADC via PS, and the address is also provided here. Please also refer to the description of this video. I will provide the address also there in order to be able to directly go to the videos by clicking on that. In previous experiments, XADC data was read using polling from the PS. But in this method, interrupts are enabled for automatic temperature monitoring. When the chip temperature exceeds the predefined threshold, an interrupt will be generated, and the CPU immediately responds to the event. It has some advantages in comparison to the first and second method. One of the advantages is event-driven monitoring. Another one is reduced CPU workload, and the other advantage is faster response to critical temperature condition. Because of all of these advantages, this method is preferred to the others. The schematic of the Zybo board is given here. It has 6 PMOD boards with the configuration of 2x6 as illustrated in this figure. The 14th of them, which is here, is indicated with 14, and it's also written on the PMOD port XADC. It is related to XADC communication, but all the PMOD ports has 2 dedicated pins for VCC and 2 others for the ground, and the 8 other signals could be configured to be analog or digital I/O. On the Zinc device on the Zybo board, as well as the mapping of these pins to the XADC input is summarized in this table. Pins J5, JA6, JA11, and JA12, as explained earlier, are connected to VCC and ground and are therefore not included in the table. Pins listed within the same columns, such as JA1 and JA7, form a differential pair. This means that the voltage applied to the ADC is the difference between the voltage of these 2 pins. As you could see, JA1 and JA7 connected to the equivalent pin of the PL of the zinc of Zybo board, N15 and N16, and then it is equivalent to the XADC pin AD14P and AD14N. As it is illustrated, it is configured in a differential mode, and in general, the 8 data signal of the PMOD port are grouped into 4 differential pairs. The XADC is capable of generating multiple alarm signals. The table, which is shown in this slide, summarizes the XADC alarm output, names, and describe the function of each alarm. For example, ALM0 corresponds to the temperature sensor alarm, while OT, the last row, indicates an over temperature condition, meaning that the chip temperature has exceeded the predefined threshold. When it exceeds a predefined threshold, it will be 1 at the output of this OT signal. The figure of this slide illustrates the temperature variation over the time and the corresponding behavior of the XADC monitoring signals. The vertical axis represent temperature, while the horizontal axis denotes time. As the temperature increases, the ALM0 signal is asserted when the temperature exceeds the temp upper threshold. This one, temp upper threshold, and triggering an interrupt. If the temperature reaches the OT upper, this value means the over temperature condition is activated. This one, this OT signal will be activated. And again, during the cooling phase, when the temperature falls below the temp lower, this value, temp lower threshold, the ALM0 signal is deasserted, which means that it goes from 1 to 0, and the interrupt is cleared. This mechanism enables accurate and automatic monitoring of critical temperature conditions, allowing the system to respond promptly and reliably. In the next step of this tutorial, step by step, I will show you how we could create a project to include interrupt while using XADC and while trying to read the data of this XADC. Okay, in Vivado, create a new project. Name it as XADC Method 3. The board, choose Zybo, next, finish. Create block design, okay. Add IP, sync processing system, run block automation. By double-clicking on this, in interrupt tab, check fabric interrupt and PLPS interrupt ports. Okay. As you could see, the interrupt port of this sync processing system will be available. Then again, XADC wizard, click on this XADC wizard. From the basic tab, you have to do some configuration. Since data is accessed through the AXI bus, the AXI for light interface is selected. To enable sampling of multiple channels, the channel sequencer should be selected here. And for continuous XADC data acquisition, continuous mode is selected here. The D clock is set to 100 MHz with the ADC conversion rate of 1 megasample per second and conversion time of 4 clock cycles. Again, check that over temperature alarm and user temperature alarm should be checked. And in channel sequencer, you have to activate based on the datasheet of Zybo board, activate via auxiliary 6. and also the auxiliary 7, the auxiliary 14, and 15. This is for channel enabling. Okay, confirm this page, and then connect the interrupt of this XADC wizard with the processing system interrupt, and then run connection automation. Okay, two extra blocks, the processor system reset and the AXI interconnect have been added to the design. Regenerate the layout by this option, and then go to the sources, right click on the block design that you already generated, create a share wrapper. Okay. In the next step, you have to add the constraint file of the Zybo board for defining the different ports that are related to this XADC. So in the constraint, right click on that and choose add source, add or create constraints. Next. You could add files if you already have it or have access to the file, but otherwise you will choose create file. I will choose a name for that, Zybo XDC, then okay. As you could see, the file is created here, and then finish. So I have access to the file. I have to double click on that. I will paste the content of XDC file of the Zybo board here in this file and save it. If you go and find the part that is related to XADC, you could see that all we have explained in this tutorial, for example, the different equivalent ports of the PL of this Zinc device on the Zybo board in 15 and also in 16, which was connected to V auxiliary 14P and N, are all should be defined in this constraint file. I should uncomment all the parts that are related to this XADC block in order to be able to impose a constraint for connecting all these ports to the equivalent of that on the Zybo board. Okay, after completing this XADC configuration, you should go again to Flow Navigator and this time choose Generate Bit3. After Generate Bit3 become completed, export hardware, include Bit3, and then launch SDK. Wait for the SDK to be open, and then in the next step we have to do some other process in the SDK to complete the project. It still needs time. Okay, in SDK, go to File menu and then choose Create Application Project. Name it as XADC Method3. The board support package will also generate it. Next, empty application, and finish. In the generated board support package, again PS7 Cortex A9 in include folder. It is still building workspace, you should wait. Okay, again, if you refer to this include folder, you could check that two header file with the name of XSysMon or something like that. Yeah, they are here. These two header files will be generated based on the configuration that you have done in Vivado. X is abbreviation for the Xilinx Smooth library. It starts with this alphabet, and Sys for system monitoring, which are the driver for this XADC. And also another one underline HW that is based on your project. You could use any of these two libraries. Okay, I will close this one and I will go to the application project, the SSRC folder, and by right clicking on that I will create a new source file with the name of main.c. I will complete the main.c code and I will explain it to you part by part. For example, as you could see, this Xilinx SysMon is added here, this library, and also an instance of XSysMon has been defined here. In another part of the code, a pointer of type XSysMon config is declared to store the hardware configuration of the XADC module. Then the function XSysMon lookup config, this one, retrieve the configuration corresponding to the target device using the ADC device ID, which is defined in the beginning of the code here. And if you control click on this one, you could see that it has been defined in another header file, which is xparameters.h. With this value, you could also check this value at the start of this code. Here, if I scroll up, this is the amount of this device ID. This one. And then if you go back to the main.c code, by scrolling down to see the rest part of the program, as you could see here, the CFG initialize has been used here in order to initialize the XADC using the retrieved configuration data. The base address of XADC register is provided through config base address, this part. If the initialization fails, the program terminates with a failure, XSC failure. In another part, you have to disable alarms before configuration. By using this set alarm enables and by taking 0 to this function, all XADC alarms are disabled initially to prevent unintended interrupts while configuring alarm threshold. In the next part of the code, the upper and lower temperature thresholds will be set. For example, with this function XSysMon temperature to raw, the 18 degrees centigrade will be converted, and then it will be set to the upper limit of the alarm. And also in the next part, the 70 degree will be converted and it will be set as the lower limit for the threshold. If the measured temperature goes outside this range, an alarm will be triggered. In the next part of the code, after configuring the threshold, the temperature alarm will be enabled, again with the same function set alarm enables, but with another value. And in the next part of the code, if you scroll down more, you could see two functions, interrupt global enable and interrupt enable, has been used in order to enable the global interrupt for the XADC module, and the interrupt source corresponding to the temperature alarm will be also enabled. And finally, use set interrupt init function to assign it to this status value. This function is for initializing and configuring the processor interrupt controller and connect it to the XADC. If the interrupt setup fails, the program will be terminated. Okay, in another part of the code, in the infinite loop, the raw temperature data is read from the XADC with the function getADC data, and then converted it into a real temperature value in degrees Celsius or using the raw to temperature function. In the next part, the core supply voltage VCC internal is read and converted to a real voltage value. The same process will be repeated for VCC auxiliary, VCC BRAM, VCC P-int, and VCC P auxiliary, and VCC P DRO, which is the PS internal regulator voltage. Again, in another part of the code, you should read external analog channels, the dedicated differential analog input channel VPVN is read here. After bit shifting, the raw ADC value is converted into current measurement, this one, and representing the board current. Again, here, as you could see, the other channel, auxiliary 6, auxiliary 7, and auxiliary 14 will be read. Finally, in the next part, all measured temperature, voltage, and current values are printed to the serial terminal with 2 decimal digits of precision using the printf. And then, if you could see, all this temperature, auxiliary, and the others will be printed in the SDK terminal. Finally, with using this function, the 1 second delay is applied so that the measurements are updated and displayed once per second. After completing the main.c file, go to Run Configuration, make a new one. All the beta stream and initialization file has been set here. Reset entire system. In the application, choose PS7 Cortex A9 and then apply. Close this page. Go to SDK terminal. Connect the equivalent COM port. But before that, you have to turn the board on. COM4 should be chosen here, and then OK, and then again go to this run configuration, or directly you could run the program on the board and then choose run. Okay, as you could see, after running the program on the board, all the temperature and voltages that has been defined in the program will be shown and printed in the SDK terminal. All these V auxiliary 6, 7, and 14, and the temperature, and also the current. Okay, the project has been finished. If I want to summarize, in this tutorial, we concentrate on method 3 for reading XADC data via AXI with interrupt. Don't forget to visit my channel, which is given here, for finding further tutorial in SoC design. Thank you for watching this video.